Hello friends, in this video we will understand asynchronous up counter. How to use asynchronous as up counter as well as down counter. Down counter we will study in next video, but in this video we will concentrate how to use asynchronous counter as up counter. And to start with this topic, let me tell you in advance that asynchronous counters can be used as either up counter or down counter only. So let us start with asynchronous up counter here. Don't forget that asynchronous counters are also called as ripple counters. See, up counter means you are counting 0, 1, 2, 3, 4, 5, 6 and so on, that is in ascending sequence. Suppose if you are counting in descending sequence, then the respective counter is known as down counter. Now popularly that we see on traffic light controllers, the counter that they are using is a down counter. So let's start with how to use asynchronous as up counter. So the basic rules we are not going to leave, that is using all the flip-flops in toggle mode, and if you remember the clock arrangement also. So let's begin with asynchronous up counter. Now to understand on a smaller skills first, I'll go for 3-bit asynchronous counter. In fact, let us start with the question. Design 3-bit asynchronous counter. So the question is, design 3-bit asynchronous up counter. So to begin, first of all you need to decide how many flip-flops are needed. It's common sense. 3-bit asynchronous counter means you require 3 flip-flops. So number of flip-flops required equal to 3. After that, let us draw 3 flip-flops. Let's use T flip-flop so that all the T will be shorted together and all of them are connected to 1. So all of them are connected to VCC. Let us assume this is flip-flop number 0. So T0 and Q0 are input and output respectively, T1 Q1 and T2 Q2 here. Now very important, that is clock arrangement. So the type of clock that I am using is a negative edge type triggering. See, when it comes to flip-flop, you can use only edge triggering, that is either positive edge or negative edge. But let me tell you, when you are using this as up counter, use negative edge triggering only. Why to use negative edge triggering? What is going to happen if I am going to use a positive edge triggering? Everything we are going to discuss, but later on. So right now what I am telling, just concentrate on the same, that use only negative edge triggering type. So what I am doing here, I have applied a clock here, that is clock pulses. The type of triggering would be negative edge triggering, don't forget that. So if you remember, I said that whenever a min clock is given to a flip-flop, then that flip-flop automatically becomes LSB. So remember, output Q0 is LSB and output Q2 is MSB. Now output of first will be, applied as a clock to the next, and then Q1 will be applied as a clock to the next, like this. So don't forget that we are taking outputs from Q0, Q1 and Q2, or from Q2, Q1 and Q0. So outputs are taken from these 3 lines, which is Q2, Q1 and Q0. Of course, Q2 is MSB and Q0 is LSB. Is that right? So now let's study this. If you remember, if a particular flip-flop is in toggle mode, what is going to happen? The output, I would say, it will keep on toggling at every negative edge of clock. That is, let's talk about flip-flop number 0 here. I'm going to discuss flip-flop number 0. Please pay attention carefully. Can I say that flip-flop number 0 is operating under toggle mode? You can observe. Yes, because T naught is connected to VCC, that is T naught is connected to 1. So this Q naught will keep on toggling, that it will become 0 1 0 1 0 1 continuously at every negative edge of the clock. Let us study flip-flop number 1. So flip-flop number 1, is it operating under toggle mode? Answer is yes, because T1 is also connected to VCC. Therefore, I will say that Q1 will also keep on toggling at every clock edge, right? But see carefully, flip-flop number 1's clock is coming from Q0. So can I say that this Q1 will keep on toggling every time this clock falls from 1 to 0 or Q0 falls from 1 to 0. So every time Q0 falls from 1 to 0, Q1 will toggle, because Q0 is acting as a clock for Q1 or acting as a clock for flip-flop number 1, because of which Q1 is changing. So for flip-flop number 2, let's have this discussion also. As you can see, T2 is also connected to 1. Therefore, flip-flop number 2 is also operating under a toggle mode, in which this Q2 keep on toggling, that is 0 1 0 1 0 1. This is what we call as a toggling. So Q2 keeps on toggling every time clock falls from 1 to 0. But from where the clock of flip-flop number 2 is coming? It is coming from Q1. Therefore, can I say that every time Q1 falls from 1 to 0, Q2 will keep on toggling. So what we have said, let's make a table out of it. And before we go to the next slide, let us summarize this again. Concentrate very carefully at flip-flop number 0. Q0 will keep on toggling at every negative clock edge of clock. Q1 will keep on toggling every time Q0 falls from 1 to 0, and Q2 will keep on toggling every time Q1 falls from 1 to 0, because Q1 is acting as a clock for flip-flop number 2. Let's make a table for a next slide. So I have made 3 columns here. In first I am drawing a main clock. Don't forget, the main clock is only given to flip-flop number 0. It has nothing to do with status of Q2 and Q1. Only Q0 is going to change at every negative edge clock of the main clock input, because Q0 will act as a clock for Q1 and Q1 will act as a clock for Q2. In third column, I am going to keep a track of the decimal count that you are getting. So assuming clock number 0, when no clock was applied, initial status of Q2, Q1, Q0, let us assume all of them are 0, 0, 0. Now, at application of every clock pulse, of course, since it is given to flip-flop number 0, if you remember, Q0 keeps on toggling. Therefore, at first clock pulse, second clock pulse, third clock pulse, fourth clock pulse, fifth, sixth, seventh, eighth, ninth, 10th, and so on, if you see the status of Q0, it will keep on toggling itself. So as I said, at every clock, Q0 keeps on toggling. Therefore, Q0 will keep on toggling like this, 0, 1. Then 1 will become 0. At third clock pulse, again it will become 1. At fourth clock pulse, it will be 0, 1, 0, 1, 0, 1, 0, 1. And this is not going to change. Let's see what about Q1. See, for Q1, who is a clock? If you remember, for Q1, Q0 is responsible, or Q0 acts as a clock. So whenever Q0 falls from 1 to 0, Q1 is going to toggle. Am I right? Therefore, as you can see, here Q0 is changing the status from 0 to 1. So for 0 to 1, it is what we call as positive edge, and therefore Q1 will not change. Q1 will remain 1. Here you can see Q0 is falling from 1 to 0. Come on, 1 to 0 is called as what transition? It is called as a negative edge transition, and for negative edge transition, Q2 toggles. Therefore, Q1 will change to 1 now. So I repeat, when Q0 is falling from 1 to 0, Q1 will get toggled from 0 to 1. Next time, as you can see, the transition is going from 0 to 1. So for 0 to 1, it is called as a positive edge, and for positive edge, it is not going to respond. Q1 is remaining 1. Then for next, as you can see, it is changing from 1 to 0. Come on, 1 to 0 is called as negative edge, and for negative edge, Q1 will change to 0. Next transition, as you can see, it is 0 to 1. 0 to 1 is again a positive edge. For positive edge, it will be in no change condition. For 1 to 0, it will become 1. For 0 to 1, again it is no change. For 1 to 0, of course, it is going to change to 0. For 0 to 1, again there is no change. For 1 to 0, it is going to change from 0 to 1. This is how Q1 is toggling, right? So don't forget, now I'm going to plot for Q2, or I'm going to write the bit status for Q2, but then it depends on Q1 because Q1 is acting as a clock and responsible for Q2 to get toggled, right? So even flip-flop number 2 was in negative edge triggering mode. In fact, every flip-flop that I have used in negative edge triggering mode. So can I say that Q2 will toggle only when Q1 is giving you a negative edge? That is, when Q1 falls from 1 to 0, Q2 will get toggled. So as you can see, the first transition, Q1 is changing from 0 to 0. 0 to 0 means no change. 0 to 1, of course, no change. 1 to 1, no scope, no change. 1 to 0, this is called as a negative edge. Therefore, Q2 will get toggled to 1. Next transition, you can now refer to the table. 0 to 0, no change. 0 to 1, no change. 1 to 1, of course, no change. But 1 to 0, again there is a change. Is that right? And again, going further, 0 to 0, no change. 0 to 1, no change, and so on. Is that right? Now Q2 Q1 status, we already have this, and now let us justify why it is called as up counter. So now you can refer 000. If you convert this into decimal, you will get 0. For 001, it is 1. For 010, you are getting 2. For 011, of course, it is called as 3. You can use 4 to 1 on top of this so that you can identify this. For 100, as you can see, there is 1 only below 4, so it is nothing but 4. For 101, as you can see, 101 means it is below 4 and 1. 4 plus 1 is 5. After that 110, so it is 6. For 111, it is 7. For again 000, again you are getting 0, then 1. Can you see that this count is repeating now? So in a way, it is starting with 0 and then it is ending up with 7, and from 7 it is coming back to 0. So let's draw a state diagram for this. As you can see, it had started with 0, 1, and so on. It is going up to 7, and from 7 it is coming back to 0. So can't you see, looking at the decimal count, it is in ascending sequence. So as we have already studied, if it is going in ascending sequence, naturally it is called as up counter. So from even the state diagram also it is clear that it is up counter. So as we have already seen in ring counter as well as in twisted ring counter, we used to count the number of clock pulses for which you are getting unique count. In this case, the unique count can be taken as 8, that is from 0 to 7. So can I say that it is capable to count how many clock pulses? Of course, 8 clock pulses. Which is nothing but 2 to the power 3, where 3 is the size of the counter, which is 3 bit. So if you remember, we have studied the types of counter, which was n is to 1 counter, which is called as ring counter. Twice of n is to 1 counter, which is called as a twisted ring counter. And the last type we have already seen, 2 raised to n is to 1 counter. 2 raised to n, what is n? Size of the counter, which is 3 bit here. So 2 raised to 3 is what? 8. Therefore, it is capable to count 8 clock pulses. So in a way, this relation has come like 2 is to 3. And therefore, I can call this counter as even 8 is to 1 counter also. So I'm sure you must have understood, even for n bit, I'll take these relations, that is, it can count 2 raised to n pulses, that it divides incoming frequency by 2 raised to n, or it acts as 2 raised to n is to 1 counter. In this case, since it is capable to count 8 clock pulses, I can say that the output frequency either at Q2, Q1, Q0 is always equal to f clock divided by 8. So I can say that output frequency, which can be either taken on Q2, Q1 or Q0, you can plot it, you will always get this relation, that is f clock frequency divided by 8. So this is how this asynchronous counter works. Don't forget that every flip-flop should be in toggle mode. The clock arrangement should be in a way that whichever flip-flop you apply a min clock becomes LSB, the last flip-flop will be called as MSB flip-flop, and so on. And the type of triggering, don't forget that I am used negative edge triggering, and outputs are taken from Q2, Q1, Q0. Remember, outputs are not taken from Q2 bar, Q1 bar or Q0 bar. Output must be taken from Q2, Q1, Q0, and the type of triggering is negative edge triggering. What is going to happen at positive edge? What if I'm taking outputs from Q2 bar, Q1 bar and Q0 bar? Every possibility we are going to discuss in the next video. For this video, this is enough to understand how to use 3-bit asynchronous counter or how to design 3-bit asynchronous counter. Thank you.